Section 7.3, the sampling distribution of a sample proportion. Let's consider the question about what proportion of U.S. teens know that 1492 was the year in which Columbus discovered America. Now, to actually get the answer to this question, we would have to go out and poll every single teen in the United States, which is obviously just not feasible. So instead, we'll take a sample. In this case, a Gallup poll found that 210 out of a random sample of 501 American teens knew this historically important date. Now, that sample result is a statistic. We denote the statistic for proportion with a variable p hat, and we get 0.42. That's estimating the population proportion, which is denoted by p without the hat on it. Since samples vary, if we talk to a different 501 students, we would get a different percentage that knew the answer to this question. The population proportion p is not necessarily equal to that same value. So if we were talking about the proportion of all teens, we could say about 42% of U.S. teenagers know that Columbus voyaged to America in 1492. However, it would likely be a bit different than that number. Now the question is, how different will it be? So to understand how much p hat varies, statistics vary around this true population proportion p, we need to understand the sampling distribution of a sample proportion p hat. When we talk about a sampling distribution of the sampling proportion, it's talking about all the possible combinations, all the possible results of going out and asking 501 U.S. teens this question. We'll get a different result every time, or at least in most cases, and we pile them up in their own histogram. Here's an example of a partial sampling distribution showing the proportion of pennies minted in the 2000s in 50 samples of size n equals 20. So each one of these p hats here is a sample of 20 pennies from our population. Okay, the population is over here. We randomly pick 20, and we find what proportion of those 20 were from the 2000. In this particular example, we got around 75%. We take another one, we get a different proportion because sample statistics vary with each sample. And if we take a third, again, it varies. We can see they range from about 35% up to 95%. And we can also see that this is taking on a unimodal and symmetric shape where most of the values are starting to pile up around 60%. That's a good estimate of what the actual proportion of values of pennies from the sample minted in the 2000s actually is. Now in that dot plot, we saw 50 p hats because the sampling distribution was created with 50 samples of size n equals 20. And those 50 samples resulted in a shape that was at least approximately symmetric. Normally, we won't take 50 samples. Instead, we'll just take one sample. And we don't know where on this curve it comes from, but we're just going to assume that it's right in the middle. So when we take a sample and get p hat, right, that's going to go right in the middle of our curve because we just take one, and that's the most likely spot that it would be. So we'll just put it right in the center there. P hat is called an unbiased estimator of the population proportion because when we take a sample, we're most likely to get a result right in the center of that curve. The standard deviation we're going to get from this equation right here. I'll be shortening it with PQ over N, since 1 minus P is just Q. When we look at that standard deviation equation, just note that the N, the sample size, is on the bottom. Which means that we'll have a different standard deviation for every single size sample that we take. A standard deviation is different for a sample of 20 items versus a sample of 21 items. And as n gets bigger, there's less variability in our sampling distribution. So if we were to increase n, let's say we make it 4 times as big. So now instead of n, it's 4n. Our sampling distribution is going to go down by half. It's going to get cut in half. All right, imagine that 4 is written instead as that 1/4 out front of that fraction. Same thing, we just changed how it's written. Okay, we could also pull it out as its own radical there. And the square root of 1/4, we can just square root the top, square root the bottom, and we can see that's 1/2. So as the sample size increases, the standard deviation decreases by the square root of whatever factor we're increasing it by. So that calculation is really the only math we have to do to create a sampling distribution of a sample proportion. However, we do need to make sure that it's valid that we use that equation. So to start, we need to have responses that are independent of one another. That's normally not the case because if we pick a person, we can't pick them again. But we get a little workaround here. As long as our sample size is less than 10% of the population size, we're just going to consider them independent. So that's the first condition we check. And the second one is called the large counts condition or the success fail condition. So in this condition, we just want to make sure that we have a big enough sample where we have at least 10 successes. We find that by doing the sample size times P, and at least 10 failures, which is the sample size times Q. As long as those numbers are at least 10, we're good to go ahead and make our sampling distribution. So as an example, according to the US Department of Transportation, 62% of all 18-year-olds have a driver's license. Let's randomly select 100 18-year-olds from the US, and P hat is going to represent the proportion of 18-year-olds in the sample who have a driver's license. So to start, 100 18-year-olds is less than 10% of all 18-year-olds in the United States. And if we do 100 times 0.18, that's our P hat. I'm sorry, 0.62 is our P hat. 100 times 0.62, that's the N times P, and N times Q would be 100 times 0.38. We get numbers that are larger than 10. Okay, so since those conditions are met, we can go ahead and make our sampling distribution, calculate the mean and the standard deviation. Well, the mean is just going to be that percentage that it gave us up here, 0.62. Standard deviation is given by the equation PQ over N, 0.62 times 0.38 over 100, square root it, and we get a standard deviation of 0.049. In part B, we want to interpret that standard deviation in simple random samples of size n equals 100. The sampling proportion of 18-year-olds who have a driver's license typically varies from the true proportion by about 0.049. Remember, standard deviation is the average distance from the mean. Mr. Ramirez's class did the penny for your thoughts activity from the beginning of this chapter. In his population of pennies, the proportion of pennies from the 2000s is 0.627. This is the population parameter, not the statistic, because it's about all of the pennies. Would it be appropriate to use a normal distribution to model the sampling distribution of P hat for samples of size n equals 16? Well, 16 is definitely less than 10% of all pennies, but if we check these conditions, so 16 times 0.627 and 16 times the complement of that, which would be 0.373, right? We'll see that this one here is not larger than 10. And because that's smaller than 10, the sampling distribution of P hat is not approximately normal, and we wouldn't want to create a sampling distribution around it. So all these previous slides are leading into this problem. This is really our objective for using a sampling distribution. So let's suppose that 35% of first-year university students attend school within 50 miles of their home. We take a simple random sample of 1,500 first-year university students, and P hat is going to represent the sample proportion who live within 50 miles of their home. In part A, we're being asked to describe the shape, center, and variability of the sampling distribution of P hat. We want to check those conditions first. 1,500 first-year university students is less than 10% of all first-year university students. And NP and NQ are both values that are greater than or equal to 10. So because of that, this distribution will be approximately normal, and we can use those equations for the standard deviation. So our shape is approximately normal. That's always the case for every sampling distribution, provided that these two conditions are met. The center is going to be the result of whatever our sample said. So in our sample, we had 35% living within 50 miles of their home. So that's going to be the center of our distribution. And then the standard deviation is given by that equation, radical PQ over N. We get a standard deviation of 0.0123. In part B, we're asked to find the probability that in a sample of 1,500 students, we get a result that's within 2 percentage points of the true value. So now that we have an approximately normal shape with a mean and standard deviation, we can create our normal curve. So we have our normal curve centered around our sample statistic, 0.35, and then we got that standard deviation from the last page, which was 0.0123. We're going to go ahead and find z-scores for values that are 2 percentage points above and below that centered value of 0.35. So 2 percentage points above is 0.37, 2 below is 0.33. Here's our z-score for that lower one. Okay, when we do the higher one, we find it's the same except it's positive. And then we're going to go and look up those values in the table to get our answer.